So this morning's speaker is Gentaro Watanabe. He got his PhD from the University of Tokyo. He's done postdocs at Narita, not here but in Copenhagen, in Trento and in Tokyo at Ryken. So now he works as a junior research group leader at the Asia Pacific Center for Theoretical Physics that's in Korea. So and he will present his talk with this long title, so please.
Thank you for the introduction. So I would like to talk about the super-free unitary semi-classic one-dimensional paradigms, and focusing on the thermodynamic properties and the critical velocity. And these are references. So this work is in collaboration with, University of Trento group, and here Levi is also one of the collaborators. And I would say, let me explain the content of my talk. First, I just give a brief introduction. Then I would like to explain the thermodynamic properties of this system. And after that, I would like to talk about the critical velocity of the superfluid. And if I have still time, I would like to explain the recent results about the loop structure in energy band of Fermi superfluids. So the study of the superfluidity has a very long history, which is initiated by 1938 by Kapitsa and Alanian and Wisner. And it has more than 70 years old, 70 years of history. And the recent, important development is the realization of the BEC of alkali atom gases. And we also have the, realization of the Fermi superfluid. And so we have both, boson and the Fermi in our toolbox. So that these cold atom gases makes us, makes the seeing is believing. What does this mean? And it means, for example, in the case of the observation of the vortex lattices, in the case of the superfluid helium-4, it is very difficult to observe the vortex core, because this core radius is Armstrong order. However, in the case of the bosons and condensate, one can realize these kind of large vortex lattices, and it is very easy to observe this very beautiful picture compared to, helium-4 situation. So this system enables us to study the superfluidity more directly and a more controllable way. So the other important aspect is cold atom gases have very high controllability, and due to the diluteness and the low temperature interaction between interatomic interaction, basically described by the S-wave scattering length only. And in the case of the two-component Fermi gases, by tuning the magnetic field using Fessbach-Resonance, one can say across BCS and BC crossover, as you know already. And here I show the scattering length as a function of magnetic field. And in the this case, in the BC regime, and we have the very strong bound pair of fermions. And the system behaves as a bosonic molecule. On the other hand, in the BCS side, we have a very localized pair size. Super pair size is much larger compared to the interparticle distance, and the situation is almost as close to the BCS theory. And the interesting thing is, in between, we have unitarity regime at which the scattering length diverges. So in this situation, we have something like very strongly interacting Fermi superfluid. And interesting at unitarity is, we have scattering length diverging, so this length scale does not drop from the problem. Therefore, the only relevant length scales are inverse of the Fermi wave number and the thermal wavelength. So that all thermodynamic quantities for uniform system are determined only by Fermi energy and the temperature. And at t equals 0 case, in uniform system, chemical potential is just proportional to the Fermi energy, as in the same as in the ideal Fermi gases. However, effect of the interaction reside in the numerical coefficient. So the numerical coefficient is modified by interparticle interaction, and for example, in the quantum Monte Carlo calculation, clarify that this coefficient is around 0.4. So next I want to explain our motivation of our study, and we want to focus on this experiment which is done in the MIT group. So what they observed is that they studied the critical velocity of the superfluid in the Fermi gas, in the optical lattice. So they create the, say, here they have cloud of the fermions, and they shine the two standing wave lasers with frequency difference of the delta nu. So that by changing this delta nu, they can move the interference pattern in this direction as controlled velocity. And so that in this situation, interference range is something like described by this way, and the S is laser intensity, and the ER is recoil energy. And in their experiment, S is rather low, so that they consider weak lattice range. So here I show their results of the condensate number as a function of the velocity of the lattice, so that they can change the velocity of the lattice by tuning the delta nu, and then they measure the number of the condensate particles. And at some point they observe the rapid drop of the MC, and they identify this velocity as a critical velocity. And here I show the velocity as a function of the magnetic field, or 1/kA, and they observe that the critical velocity is maximum around the unitarity. So their results, suggest that superfluidity is very robust in the unitarity regime. So this is.
Did they estimate the temperature there?
Sorry.
The temperature of the cloud.
Temperature is almost zero. It is very difficult to measure the temperature, but as far as they observe, as far as in the reference they say temperature effect is very low. But according to their paper, they also said they need some dissipation mechanism to observe the energetic instability. So they said that their system has enough this dissipation mechanism, but the temperature effect is quite low.
Why do they need dissipation?
Because they observe the energetic instability. So if there is no energy dissipation, the system stays in the higher energy state.
So how do they measure the critical velocity? How did the condensate number?
Yeah. So another motivation comes from the neutron star situation. And this kind of system can be also mimic the situation of the neutron star, inner crust of the neutron star. So that in the specific region of the neutron stars, matter consists of neutron-rich nuclei immersed in the superfluid neutron gas. So that this black sphere represents neutron-rich nuclei, and this white region describes the superfluid dripped neutrons. And so that this black nuclei consists of normal neutrons and protons, and this blob acts as a potential for this superfluid neutron gas. And there is also a very interesting phases, which is called nuclear pasta phase, which is rod-like or slab-like nuclei. So here we can have some spaghetti-like phase, and in some density region we can have lasagna phase. And for example, if we focus on the lasagna phase, so the superfluid neutron gas in the lasagna phase is very similar to, say, superfluid of the Fermi atoms in the one-dimensional optical lattice, because this slab-like nuclei act as a potential for the, say, drip neutron, superfluid drip neutrons, which is very resemblable to the, say, experimental situation.
But you're studying the flow in the plane in that case, not across the planes, right?
So we study the, say, perpendicular to the plane.
How you want to look at that? In neutron stars, you want to look at that state?
Sorry?
You want to look in neutron stars as that state?
Some say in some sense, say, cases.
Because that flow is much more difficult.
Yeah, that's true.
So it's much easier to flow this way.
Yeah, but in this case, say, effective mass is already, say, 1. And,
We have a big energy barrier there to go for open normal state.
yeah.
Superfluid state, normal state, superfluid normal state. So how you don't understand what kind of flow you're going to study there?
Yeah, that is true. But I say, this is just say, we do not really study this situation in our say, paper yet. So let me explain our results of the thermodynamic properties in the one-dimensional lattice case. So that we consider the, say, one-dimensional optical lattice, which is given in this form, and the S is, say, less than 5, taking into account of the, say, experimental situation, and we focus on the unitarity regime at 0 temperature. And we want to study the effect of the lattice on these basic thermodynamic quantities, chemical potential, and the incompressibility and effective mass. And so the chemical potential directly reflects the resistance. And this incompressibility and the effective mass affects the collective oscillation in the sound velocities. And this effective mass also represents a tunneling rate between wells and the bandwidth.
So compressibility. What it means? Okay, it's inverse.
Inverse, yeah. So that we consider the weak lattice regime.
Can you go back? For the unitary case, you have dependence on the density alone of the energy density. So why do you specify T as well? See, this is unitary gas is determined by density alone. So you have the two arguments, N and P, pressure, right? I don't understand.
No, not pressure. It is, let's say, condensate flow, momentum of the flow, superfluid flow.
So where do you get that dependence from?
By using the Bogoliubov equation, we can input the, say, superfluid flow.
You're going to show that? You're going to show that?
Yeah.
And in the lattice you also have the length scale for the lattice spacing, so I mean that's the...
Very bad notation, yes.
So is the effective mass a tensor or it's just a number? Does it have an anisotropy due to the lattice?
Say we consider the superfluid flow perpendicular to the lattice. Yeah.
So some kind of effective two-dimensional theory, or?
So that we consider three-dimensional system with one-dimensional optical lattice,
Right.
and the flow is perpendicular to the lattice.
So effectively two-dimensional planes coupled together is by the potential.
Yeah.
These are two-dimensional planes.
So the V is the direction of the flow. So that we consider the weak lattice regime, so it is not very good to use say Hubbard-like type binding approximation, and we use the Bogoliubov-Vijan equation for this study. And we assume the say order parameter have the say block-like form, and the P is the quasi-momentum of the say superflow. And using this ansatz, we can derive the say Bogoliubov-Vijan equation with the Hamiltonian of this form. So that here we have P. And we solve this equation together with the same self-consistency relation and gap equations and the number equation. But also hydrodynamic theory is quite powerful at some situation and very useful. So the hydrodynamic theory is valid at which the length scale of the density change is much larger compared to the heating length. So in this situation, we can treat the system as using the local density approximation, and around the quasi-momentum equals P equals 0, we can say write the energy density in this form. So this is kinetic term, and this is just P equals 0 contribution. And from the continuity equation, the Euler equation, and with the say approximation of the potential is much smaller compared to the say Fermi energy, we can derive the say density and the position-dependent density and the position-dependent momentum. And from this expression, we can calculate the average energy, and from this, we can also calculate the incompressibility. So that here I show the result of the incompressibility first, and please just see the lines, and these points are calculated by different regularization schemes. So for now, just please see the lines. And you can see that this I show the incompressibility normalized by the uniform case as a function of the EF over ER. EF is the Fermi energy for the same density corresponding to the ideal Fermi gases, and the ER is the recoil energy. And you can see that there is a maximum around EF over ER equals 1, which is very different from the boson case, in which if we increase the density EF over ER, and the system becomes more and more uniform, so that in the case of the boson, the Kf over incompressibility continuously, monotonically decreases and approaches to 1. And you can see that there is a very rapid reduction at low densities, and this is due to the effective molecular formation induced by the lattice potential. So that if we have lattice, even though in the uniform case there is no bound state, but if we have lattice, both fermion pairs can form the bound state and the system behaves as a boson-like. Therefore, incompressibility scales as n, not n2 over 3, and then it goes to 0 at low density regime. And at higher density regime, says hydrodynamic theory is valid, and this hydrodynamic expression is shown in these dotted lines, and you can see the Bogoliubov-Vijan result is very consistent with this expression. And next, we show the result of the effective mass as a function of the EF over ER. And in the case of the bosons, for example, S is say laser intensity, and S equals 5, M star is 1.9 or around 2. However, in the fermion case, we have around more than 10. And this enhancement of the effective mass is due to the formation of the bound pairs, because effective mass is proportional to the inverse tunneling rate, and which exponentially depends on the mass of the tunneling instituent. Therefore, we have very large enhancement in the fermion case compared to boson case.
Is there also a normalization of the Z factor? The quasi-particle weight.
So the interaction string, you mean?
So this is an effective mass for bosons or for fermions as well. So you mentioned fermions, right?
Yeah.
So I assume there is also the z factor, renormalization factor.
This is not for the quasi-particle. So, it's the second derivative of the energy with respect to the collective momentum. So it's not the quasi-particle, it's the collective mass.
Sort of hydrodynamic effect.
Yes.
Is it just superfluid stiffness?
Sorry.
This is just superfluid stiffness.
Yeah.
You know, when you have small Fermi energies,
Yes.
you see, I'm not entirely sure I understand the diagram correctly. Does it mean that you have localized the Fermi gas in different potential wells and the Fermi energy is much lower than the height of the potential?
Yeah. So that in that here I show the circle which is calculated by the two-body case. So that we put the two-body fermions in the orbital lattice and calculate the effective.
So essentially you have isolated pockets of
Yes.
fermions. So how do you have the flow from one to another? It's tunneling?
Yeah.
It's tunneling.
So that's I said before. So that this is obtained by the two-body results using just solve the Schrödinger equation in the optical lattice, and our BDG calculation is consistent with this result because Schrödinger equation correctly describes as a intermolecular correlation, intramolecular correlation.
But the flow there should be very small, right?
Yeah.
It's exponentially small,
Yes.
correct?
Yeah.
Yeah.
And the bandwidth is very narrow. And in the high density regime, we can also derive the hydrodynamic expression, and the probability design equation result is also very consistent with this result.
Do you self-consistently determine delta of z?
Sorry?
So in Bogoliubov-Dejean you had some gap,
Yeah.
delta of z.
Yeah.
Is it determined self-consistently,
Yeah.
or it's an answer?
Yes. It is self-consistent.
And is there any non-trivial dependence on z, or it just follows the lattice pretty much?
So that in this regime, say, yeah, it depends on the density regime also, and the current. So that if we go to the band edge, so that if I have this regime, system will almost behave as a local density approximation. So that it is quite trivial. Delta, say profile of the delta is very trivial. But in the lower density regime, situation is very different.
So you're assuming that the pairing constant is independent of the potential when you solve Bogoliubov-Dejean equations?
Probably, because otherwise it won't make sense. The calculation won't make sense.
Sorry, could you say that?
I'm asking if when you solve Bogoliubov-Dejean equations, you know, they have a self-consistency with the pairing constant. So you
Yes.
assume that the pairing constant is independent of this potential.
Independent.
Independent.
The calculation actually it's mean field the other one, is it correct?
Yeah, it is mean. So however, you can see that this point is say two-body Schrödinger equation. So that even though Monte Carlo calculation, there should be each result should be coincide with this one. And in the high density regime, we have hydrodynamic expression. And in the case of the Monte Carlo result, 1 plus beta is modified. So that this part slightly increases. But the basic picture does not change. And maybe in the lower density regime, enhancement of the effective mass is larger in the Monte Carlo results because they have more, actually, they can incorporate the attractive interaction much more compared to the negative.
Do you ever have the regime when the size of a Cooper pair is larger than the sort of wavelength of your lattice?
Yeah, so for example, around this region, the EF over ER is basically something like that. So that if we go to this regime, lower density regime, say Q graph is determined by the lattice constant.
Shouldn't it just basically ignore the lattice because you can just average that out to zero in some sense? When you have, well, when the size of a Cooper pair is so large, wouldn't it just feel the lattice as some kind of effective?
It won't penetrate from one potential well to the other. It would be a two-dimensional gas in that case, because the potential bearing is very high. So essentially, the fermions are allowed to move only in a plane.
Compared to what?
You see, they cannot go from one well to the other, because the energy bearing is very high. So even though that's true what you are saying, you see that they won't feel the next potential well effectively. It's exponentially suppressed.
But I thought the lattice was actually proportional to ER, right? So the strength of the lattice, and S, let's say, could be of order 1. So
Yes.
this parameter is basically, well, the ratio that we're talking about. So if the lattice is very weak, so why would you possibly get decoupled planes? You'll just get effective band
If you
structure.
go all the way to the left, you see, then it's the regime you're talking about.
Okay.
But there is a significant overlap to sustain the superfluidity. It should be.
No, but probably Victor means, do you ever have a regime where the size of the Cooper pair in this direction, in the direction of the lattice, is much larger than the
This
lattice
is,
mass?
this is.
Well, I think you should simply plot the pairing field as a function of z, and then that will answer the question. And I think it's exponentially suppressed, actually. And that won't happen. Do you have a plot of the profile?
At present, say,
For very small EF over ER?
present I do not. Yeah, I can show you later. So the consequences of this incompressibility and effective mass, we can see see this effect in the sound velocity, and we can also observe this effect in the collective oscillations in the lattice plus trapping potential system. So, for example, in the actual dipole mode, probes the effective mass, and the radial breathing mode also probes the incompressibility. And the effect of the equation of state can be can affect the coarse grain density profile. So let me explain a little bit detail. So here I plot the result of the sound velocity as a function of EF over ER. And you can see that very rapid reduction in the low density regime. It is due to the incompressibility, basically. But except for this regime, we can see that the density dependence is very smooth. So even though cloud has inhomogeneous density profile, maybe we can expect the sound can propagate through the cloud, except for the very edge of the cloud. And if we increase the lattice potential, laser intensity, sound velocity decreases. This is mainly due to the enhancement of the effective mass. And we can also measure the effect of the lattice in the collective oscillations. So that we consider the harmonic trapping potential plus lattice system. Harmonic trapping potential is the axial symmetric, we assume. And we say dipole mode of the z direction probes the effective mass. And using the sum rule, dipole oscillations we can see can be written in this way, and the m star bar is the volume average of the m star over the whole cloud. And suppose if we have, say, central density of the cloud less than around EF over R equals less than 1.5, meaning lower bound and the upper bound of the, say, omega d is lower bound is determined by this maximum point, and the upper bound is determined by this unit EF over ER zero point. And using this answers, we can reasonably estimate the, say, collective oscillation frequency. And for example, in the S equal 5 case, we have 0.3. And we can see that there is a very significant reduction of the oscillation frequency induced by the lattice potential.
Did they look into these dipole oscillations experimentally?
No.
Can one interpret that as a fact that the system became essentially two-dimensional instead of three-dimensional in that case? And then the oscillations are actually, it's a two-dimensional plane, which it vibrates like this. It's not the same thing as the three-dimensional gas.
It's not.
I'm talking about the last line there. Yes, it's the ratio there is about 0.26.
So this oscillation frequency just we consider as a axial motion, not the radial motion. And
you mean along the z direction,
yeah,
right? So is it because you see the plane actually it's very stiff there and it cannot do much? And and it's actually it's a two-dimensional problem. It's basically because you confine it. You see the system is confined. It's seriously in the z direction there.
But S equals of order 1, so it's not very purely two-dimensional situation actually.
Well, EF over ER is more similar than 1 there.
If we go to the very low
Yeah.
density, it can be.
Yeah.
But it's not insulated, so it's still, there's still tunneling.
Yeah, but it's exponentially suppressed.
Well, these lattice steps are not very extreme. I mean, this S equals 1, I mean, that's pretty low still. I mean, there is suppression certainly, but I think, I mean, to get it really
That's
suppressed.
equal to 1, it depends what the ratio EF over ER is. If it's much smaller than 1, then it would be exponentially suppressed. You know what I mean?
I mean, S is the lattice depth, isn't it?
Yeah.
And at least with bosons, I think, I mean, you get into this exponentially suppressed regime when S is substantially bigger than 1. So I mean, it's like 10 equal energies and above that. So this is somehow much more shallow than the norm.
Well, if I understand correctly, so myself I might not understand correctly. EF over DR, you see, it's smaller than 1, and when S is equal to 1, actually that's the height of this is the height of the barrier, this is ER, and E farm it's below. So in that case, you see, you have significant, I mean, you have tunnel.
If you have zero density, F is 0, but you can still have high tunneling with the two independent parameters. EF knows about density.
Why would you have enhanced
Just for a single particle, you have non-exponentially suppressed tunneling and 0 EF.
So why can't you just do, some sort of band structure analysis? You have a lattice potential.
No, this one they did, actually.
And just label everything with the band index.
No, this one they did, you see, but it doesn't show those results.
Well, I'm sure there is a limit when it crosses over to 3 dimensions, when the lattice is weak.
No, but they'll show these details, but this one they did.
I'm just not sure how this picture of decoupled planes arises. This is sort of strange.
So this is EF over ER, and the S equals, say, 1 and a 2.5 case. So the 2.5 case, we have this, say, band value. S equals 5, it is rather smaller compared to this one. But this region we have, say, still significant amount of the bandwidth compared to the S equal 1. So the previous this is the S equal 2.5 case, and And the EF over ER for one case, we have say still compared to S equal 1, there is significant boundary. So that I think this case it's not very say okay say the assumption of the superfluidity is not very invalid. It is still reasonable. So in the case of the radial breathing mode, it can prove the incompressibility. And if we consider the cigar-shaped trap, omega z is much smaller compared to omega per. And without the lattice case, say radial breathing mode is given by this one for the fermionic polytropic index. However, if I increase the lattice, system behaves as boson-like, and therefore omega changes in this way. And there is 20% enhancement in omega. And effect of the equation of state can be seen in the coarse-grained density profile. So using the local density approximation using the say omega local chemical potential calculated by Bogoliubov-Jan equation, we can solve the say so we can calculate the local coarse-grained density profile with fixed number of particles. And for this calculation, we consider the say MIT experimental parameters in MIT experiment. And this is a result for x equal 5 case. And for demonstration, we plot the x equal 5, and the blue curve shows the no lattice case. And this is the chemical potential as a function of the density, and it scales as n to the 2/3. And however, if I have lattice case, the chemical potential is all quite close to the linear dependence of the density. And affected by this result, we can see that very drastic modification of the density profile from the say Thomas fermionic parabola to the inverted parabola. Fermionic Thomas Fermi density profile to the parabolic density profile. So let me summarize for now. And we studied some dynamic quantities of the unitary fermions in 1D optical lattice. And we can see the effect of the lattice in the very low density regime especially. And formation of the molecules, and there is also band gap effect, which comes from the quasi-2D dimensionality. And we have the linear density dependence of the chemical potential. And we see the reduction of the incompressibility in the low density regime, which is due to the scaling of the incompressibility proportional to the density. And we can see the drastic increase of the effective mass. And this effect can be probed by collective oscillations. And we saw that there is a large change in the coarse-grained density profile affected by due to the say, change of the behavior of the chemical potential. So the next thing I would like to explain our recent result on the critical velocity in the one-dimensional optical lattice system. And in 1945, Landau considers a superfluid in the base cell. So that if the velocity is high enough, kinetic energy of the flow can go to the excitations. And if there is a dissipation, kinetic energy of the superfluid can be dissipated by a creation of the excitations. And this critical velocity is a Landau critical velocity. So that here I write that E0 represents the energy in the condensate, rest frame of the condensate, and the epsilon P is the excitation spectrum in this frame. And if we go to the moving frame, if we go to the lab frame, and this, due to the Galilei transformation, we have the Doppler term. And this can be seen as the excitation spectrum in this frame. And the Landau criterion of the uniform system is the situation at which this becomes zero, and which is written in this form, in a formula 3. So we know that there is a, say, for example, weakly interacting Bose gas, and we have Bogoliubov spectrum, which is written in this way, so that there is a linear dispersion in the low momentum, and the high momentum we have, say, a single particle like a quadratic dispersion. And in this case, say, Landau critical velocity corresponds to the tilt slope of this part, which corresponds to the sound velocity.
Can I ask you a question? So Landau criterion applies if you can transfer arbitrary momentum, so you assume that there is some short range disorder or whatever. So in optical experiments, it's typically not the case. You typically don't have any disorder. So I just want to understand your setup. So are you assuming there is disorder? Or because in a uniform system, you can have arbitrary velocity, infinity, and still nothing is going to
Momentum
decay.
conservation also. Inside.
Hmm?
Basically, momentum conservation, or the disorder which provides the momentum.
Yes, but it's not enough to have disorder in short-range disorder. You need to transfer basically arbitrary momentum. And these systems are so clean that it's not like unusual helium or whatever.
We have, say, lattice potential, and the lattice work as a pattern.
Lattice gives you only a specific momentum in units of 2 pi over a. So Landau criterion you cannot apply. Because Landau criterion really assumes that you can transfer arbitrary momentum. Lattice momentum just assumes that I have really infinitesimally weak lattice with infinite periods. So it's like you have nothing. I think you have to be careful.
But if you have finite temperature and some interactions, wouldn't it act basically the same way?
Yeah, can this be
No,
just
but then you have
nonlinearity?
to.
So
No, but
realistically, in real life, you have finite temperature, you have interaction.
but there are again two regimes, so you can think these interactions can be some Bogoliubov-like modes, and those will be taken by superfluids. So basically, you have temperature in the framework in the velocity center of mass frame of superfluid, and those will not be like disorder. Or you can have another regime, at least experimentally, when this thermal part is stopped by the lattice, and then it acts more or less like quasi-particle, but it's quite complicated.
But quasi-particles always interact. Can't you?
It's hard to separate, because quasi-particles are part of the superfluid, so how you separate quasi-particles from just waves?
But they're not non-interaction.
So the according
If
to
you
the
have a normal part and you have different velocities between normal and superfluid, you cannot predict anything in general form. You must solve the problem.
Yes, because normal part can be part of fluid if it's long wavelengths like that. I'm just thinking that if you don't have disorder like in lattices, so the fact that Landau velocity is equal to some value might not be really informative.
so that in their experimental situation in the MIT, which I mentioned, they said there is a significant number of say thermal part.
So you assume that thermal
guarantees,
part.
dissipation source.
Okay.
But
These experiments are not so clean because the optical lattice is not perfectly straight, it's curved. So it's not quite
But it's
perfect.
also long wavelengths. So
Yeah, but it's not that long because they have 10 periods, it's already curved like this. So it's really not clean.
Yeah.
The experiment, it's not that clean as you would like to.
Yeah, I understand.
and the lattice also have say inhomogeneous.
Then the Fermi energy varies along this direction because here you have less and here you have more, and so it's pretty inhomogeneous.
But you can, I mean, at least at small finite temperatures, you can do numerical simulations, and you see that there is very little damping, at least not in Landau velocity.
So there is, our motivation is, say, theoretical side. There is a paper by Convesco and Kagan and Stringari, and they consider the critical velocity for the uniform Fermi superfluid, and they show the critical velocity as a function of the 1 KFA. And in the BC regime limit, we have weakly interacting bosonic molecules. Therefore, critical velocity is given by the sound velocity as in the lambda criteria. And in the case of the BC limit, Fermi gas with infinitesimal small gap. The system consists of Fermi gas with infinitesimal small gap. Therefore, critical velocity is determined by the pair breaking velocity. And then in between, at unitarity, we saw the maximum of the critical velocity around this region. And experimentally also, they suggest that this maximum of the critical velocity around unitarity. And in their experiment, they also study the critical velocity as a function of the lattice depth at unitarity. And then you can see that there is a rapid reduction of the critical velocity with increasing the lattice strength.
But if the lattice depth is very high, so effectively you have 2D. In 2D you should have some Kosterlitz-Taulis type physics where critical velocity, strictly speaking.
Lattice is not very high. It is.
But do you not have two-dimensional superfluid effectively?
He just considers transfers,
Yeah.
not in plane, not in plane superfluid, otherwise there would be something.
And I think all these lattice steps are such that you are not in this really in this
So it's not connected with what you were talking beforehand, right? When you said they were, in fact.
Yeah, so it is very low lattice regime. So there is a significant superflow across the lattice. There is still a three-dimensionality.
So it's opposite to the limit that we consider.
Yeah, it's opposite.
I would like to note in this relation that this experiment does not correspond to any perfectly to any theoretical models, because it is not only the motion of the lattice, but lattice appear on the left side, for example, and after increases and after disappear on the right side. So this is a little bit different.
Yeah.
We must
I
take this.
I will show this later.
Okay.
So in the zero, lattice limit, they observe something around this value, which is, in the sound velocity it is 0.37 Fermi velocity, and it is not very accurate, but the consistency is around 20 or 30% answer. So the setup is as follows. We consider 4 cases, and which means we consider bosons and also unitary gases, and we consider 2 potentials. One is periodic lattice, and the other is a single barrier. And we introduce a length scale of the width of the lattice to show the result in a unified way. And in the case of the single barrier case, width corresponds to the just width of the single barrier. And in the case of the periodic potential, we take half width full maximum. Full width half maximum as a length scale of the width of the barrier. And in this situation, hydrodynamic theory also provides a very powerful and useful expression. And so that in the case of the local density approximation is valid, energy density can be written in this way, and we can have an equation of state and the local sound velocity. And the current density is constant, it does not change the spatial dependence. And within the local density approximation, density is the smallest at the potential maxima, which I write z equals 0. So that from this velocity is the largest at z0. Therefore, we can see the critical velocity as follows. And so the critical velocity is given by the situation at which local flow velocity equals to the local sound velocity, which reduced to the, say, this expression. So that you can see that this expression, JC, is a critical current, and the new JC is a chemical potential at the critical situation. And this expression only determined by the Vmax, which is the maximum point of the maximum value of the potential. And the other place, potential in the other part does not contribute to the problem. Therefore, this expression applies for any potential, both for fermions, and the fermions in the case gamma equals 2/3, and the bosons gamma equals 1. However, in the non-LDA regime, we cannot use this expression, and we have to calculate the critical velocity using a different scheme. And this scheme which we use is a hydrodynamic analysis for excitations, which is different from the local density hydrodynamics as mentioned before. And energetic instability is created by the long wavelength excitations, and therefore hydrodynamic analysis of the excitation is appropriate, which means long wavelengths compared to the say, lattice constant. How can I say? Hydrodynamics means say excitation of the wavelengths is much longer compared to the lattice constant, and we can treat say starting from the Euler equation, the continuity equation, we can derive the dispersion relation for the long wave phonons in this way, in this form. So that we have two terms, and when the say first term it becomes larger compared to the second term, we have say energetic instability because omega can be negative. And this situation gives say a Landau critical situation in the say corresponding to the uniform system. And when the inside of the square root becomes negative, we have say complex excitation. Therefore, we have dynamical instability in the long wavelengths. So here I show that
when this is unstable, what's the new state?
Sorry. So the phonon, say, superflow dissipate into the phonons.
But so I mean the ground state is unstable. Dynamic instability or something.
Dynamical instability means if I have say this situation, very small perturbation say increases exponentially by time. So
then what is the final state?
Say we cannot say it from here. This superflow situation becomes completely destroyed by time. From this, we cannot say any final state. So here, I show the schematic picture of the analysis, and the right-hand side is plotted by red curves, and the left-hand side is plotted with the blue curves. And the uniform system, where the dispersion is quadratic, it corresponds to the, say, these dotted lines. And when these two curves say coincide, we have the say critical situation. And this how can I say? Y intersection corresponds to the sound velocity, and this slope of the say, red curve corresponds to the 1 over effectiveness. And if I have larger lattices, dispersion becomes more sinusoidal. Therefore, this say blue curve starts to hit some zero, where the second derivative with respect to the p becomes 0. And this red curve at the band edge becomes 0 because there is a 0 slope, which corresponds to 0 height. And if I increase the lattice potential, this intersection reduces, and this part approaches to the say, half of the brilliant zone. And also this field reduces because this is inversely proportional to the effectiveness. Therefore, critical situation corresponds to the half of the brilliant zone in the very high lattice situation.
So this energetic instability, isn't it the same point with where the Bogoliubov approximation breaks down, basically, in some sense?
Sorry?
So are you using any sort of Bogoliubov approximation? What do you actually
this is a say, hydrodynamic say, analysis for the stability.
But what equations do you solve?
So that we consider long wavelength excitation only, and which is say relevant for the energetic instability.
Is it a kinetic equation, Boltzmann equation?
So that this expression comes from just hydrodynamics.
So you just write it down by hand, phenomenologically, or it's related to a model?
This is quite general. So that it comes from the continuity equation and the Euler equations.
So the frequency of the excitations remains real and energetic instability, right? It doesn't become complex. It's not linear. It's not instability in linearized dynamics.
It is actually linearized
it's not
with respect to
instability.
the perturbation.
But since frequency remains real, there is no instability in linearized dynamics.
It's negative.
Yeah.
But it's still there's no
Because of imaginary part.
there's no imaginary part, so there is
No.
fluctuations don't go.
It's an energetic instability.
Read the last line.
We consider energetic instability, not the dynamic.
Read the last line on this line there.
Yeah, I understand, but I'm just
Then
saying.
it becomes complex.
No, that's for dynamical instability. For energetic instability, it just becomes negative.
But I think there is some confusion. So I don't think there is a difference between instabilities, because for dynamical instabilities you solve full GP equations, so flow equations, with the lattice, and then you linearize with them.
Yeah.
For energetic instability, you solve first equations without assuming that any perturbation, lattice or impurity, and then you linearize. You cannot get imaginary frequencies because you have Galilean invariance. So I think if you want to get imaginary frequency, you have to put impurity by hand. Then solve Gross-Petaevsky equation with impurity and linearize around it.
But wouldn't
And
you
then you'll get imaginary frequency.
But wouldn't you get instability if you just included non-linearity? That's what I was asking.
No, because you have Galilean invariance.
To make something non-uniform.
You need to make something non-uniform, solve GP equation, linearize around that, and most likely you will get imaginary
This is
frequency.
Fermions.
Well, then not GP, but
But
some
actually
other
kinetic equation, that's what we need to write.
kinetic equation.
With collision integral, any collision integral will do it. I don't think impurity is necessary.
You need to break Galilean invariance. You need to have some static perturbation.
So this is a result of our analysis. And here we plot the sound critical velocity normalized by the sound velocity for uniform case as a function of the say, potential height. And so here I show the say, local density approximation, and if I increase the say LKF, which means say lattice constant is much larger compared to the say healing length, it goes in this direction, and then you can see that the say result approaches to the local density hydrodynamic field. And in some state, in the L times Kf is much smaller than 1. In this case, the system is insensitive to the potential because in this system, density variation is forced to be periodic with the period of lattice constant, and it is very hard to excite this kind of density modulation when the healing length is longer compared to the lattice constant. And And in the very, say, high lattice situation, and the situation is almost, say, band dispersion of the band structure is, say, almost sinusoidal. Therefore, in this case, critical velocity is only described by determined by the effective mass. And this curve is analytical, semi-analytic result, which is given this way. And here I summarize the situation of 4 cases, bosons and fermions with barriers and lattices. And there is no large qualitative difference between fermions and bosons. And however, between barriers and the lattice case, there is a very large difference. And you can see that in the case of the lattice potential, we have the plateau for the low L-back psi. However, in the case of the single barrier case, we do not have this kind of plateau. So let me summarize 3 regimes. So we can identify 3 regimes in this plot for the lattice system. And then there is a situation where the hydrodynamic flow in the local density approximation is a very valid case. And there is another regime which we have plateau, where the healing length is much smaller compared to the lattice constant is larger. The lattice constant is smaller compared to the healing length. And this region, and the other region is there. So that we have, say, weakly coupled superfluid separated by the lattice potential. And let me just briefly explain the experimental situation. Here we compare our calculation with the experimental results. Suppose we take typical fermion energy of the experimentally created cloud is given by the number of the total atoms in the trap. So in this case, EF over ER equals 1. And then for this parameter, our calculation result is this way, and the experimental result is this way. And you can also see that there is significant, say, discrepancy between the 0 lattice strength regime compared to the sound velocity. And the other parameter which we can think of is typical Fermi energy of the cloud is given by the density at E1 to the E minus squared beam weight. And this is a ansatz in which experimental analysis has been used. And in this case, EF over ER equals 0.5, and our Bogoliubov-Giant result is something like here, and the experimental result is something like here. And you can see that at 0 lattice strength, the experimental result is more or less consistent with sound velocity. However, there is significant discrepancy between the Bogoliubov result and the experimental result. And the other, so this region would be, as left ordered before, there is a cloud, and there is a lattice potential. However, lattice potential is not very uniform. And therefore, the lattice potential moves from this side to, let's say, disappear in this side. And therefore, this region not only is a typical density area, we have something very messy things around in the side skirt. So the other setup, which would be better for measuring the critical velocity, would be annular drop, something like that. In this case, this kind of homogeneous lattice potential can be removed partly, at least. So that I would like to summarize this section. We studied the critical velocity of the Landau instability for one-dimensional periodic potential and single barrier case. And we derived the expression applied for any potential in the hydrodynamic regime. And we can also observe the say, significant reduction of the critical velocity induced by the lattice potential with increasing L-box size heating in the hydrodynamic regime, say approaching the hydrodynamic regime. And there is a large difference between the single barrier and the periodic potential case. And in the case of the single barrier case, there is no plateau of the critical velocity as a function of the say, lattice potential. On the other hand, there is a say, large plateau at smaller L-box psi for the periodic potential case. And this is due to the say, in the case of the periodic potential, density modulation is forced to be periodical as a function, say, in the period with the period lattice constant. However, say when the L-box psi is smaller, it is very energetically expensive to have such kind of situation. And this is basically this is yeah. So this is the end of my talk. Yeah, thank you for.
Is it like you start from the unitary gas and then you apply the strong periodic potential of the order of the Fermi energy? Is it obvious that the gas will remain unitary when you apply the potential of the order of the Fermi energy, because you would tune that
scattering property.
No, you would tune that zero energy level, the start shift, up or down, and they'll become non-unitary, and then all properties will change.
I have no.
The unitary properties.
Answer can be given in some formal way, because when you make calculation of Bogoliubov-Dejean equation, you will change the condition magnetic field, for example, and this will given magnetic field you will obtain some answer. And where are you near the old Feshbach resonance, you will obtain answer. You can follow values only. If there is no singular point in Feshbach resonance, not in the uniform body, not in the lattice.
Right, but then if you're away from the resonance, then I would expect that, for example, the coupling constant in the Bogoliubov-Dejean equation, you have to calculate using the Bloch wave functions, which depend on the amplitude.
Yes, you must.
So, right, but then I asked the question if you guys take into account the effect of the periodic potential on the coupling constant, because then it becomes more complicated.
I don't think it's needed in this case.
No, that's my question. So, what is a small parameter here? Why you can neglect all
You have a
this?
white Feshbach resonance
Huh?
here. You have a white Feshbach resonance.
Why?
Two, you see the magnetic field here, it doesn't change basically from the resonance value because it's an optical trapping essentially. You see,
No, I mean this is the model, right? So
no,
consider a
the
unit.
trapping is optical, so it doesn't modify the interaction between two atoms. So the interaction stays the same.
But you have the
What-
field. You have the electric field which acts on.
It's
on
not an
Okay,
electric
I
field,
would
it's a magnetic
add
field.
that, of course, you must have lattice period larger if compared to size of the interaction of the, but not with the, but nothing more. Yes.
No, I completely, you don't have those effects you have feared about.
Why
I
not?
don't think you should worry.
I mean, you put V in the Bogoliubov-Dejean equation, so that's a potential. So you have a shift of the level, right?
The strength of the interaction, it's controlled by the magnetic field, which is imposed from above, you see, which is basically uniform. On top of that, you put laser fields,
Right.
which trap the thing.
Yeah.
They don't modify the position of the resonance. Those.
No, I'm talking about the periodic potential.
Yes, you see, this is the trapping field and the periodic field. Don't modify.
Well, it depends how strong they are.
Yeah, but-
If you really, depends how
And
strong they are. If you
Your
really
V is
confine
of the
them,
order of the
course,
Fermi
you will
energy,
modify them.
Of
so
course, the period and strength must be smaller compared to van der Waals size and energy.
right.
This-
So
this
that's my question.
condition
Really,
is-
is a small parameter.
Yeah, it should
but
be-
not more.
Okay.
More questions? We already had a lot of questions. Fine, so let's thank the speaker once again.